Welcome back, Night Owls. This is Dr. Nighttime, and tonight I'm going to go through a requested problem. So I'm asked to show that the limit as x approaches 1 of 1 over x goes to 1. Now, intuitively, we could say, well, let's think about the graph, and we can see this graph looks continuous. And so that should mean, right, that okay, you plug in 1, you get a y value of 1. You should be able to just say, well, since we can see the graph is continuous, then obviously the limit has to equal the function value at that point. Unfortunately, it doesn't work that way. Now, you can't let the graph do the proving for you. The algebra has to do the proving for you. However, the graph can help direct your thought process, and this is something that we'll be doing throughout the course of this video. But yeah, what we want to prove for this limit is that we have to show that for any positive epsilon, there exists some positive delta, such that as long as x minus 1 is between negative delta and delta, that will imply that 1 over x minus 1 is between negative epsilon and epsilon. That means wherever we set these green horizontal lines, these have a tolerance of epsilon to either side, you can come up with lines that are that surround this point and say, as long as you're within these bounds, you'll be within these green bounds. This gray dotted line, that's there because the restriction to the left is tighter than the restriction to the right. So when we're actually saying x minus 1 is between negative delta and delta, this is x minus 1 is negative delta. This is not x minus 1 is positive delta. This one is. We have to, the bounds have to be symmetric around the point that we choose. But okay, so we start with our rule 1 over x minus 1 must be between negative epsilon and epsilon. And we can add 1 to both sides. Now, weird stuff happens when we try to take this reciprocal. We have to ask ourselves, the numbers that we're reciprocating, are they positive or negative? Because think about this for a moment. 2 is less than 5, but 1/2 is more than a fifth. Negative 2 is more than negative 5, but 1/2 is less than negative a fifth. But suppose 1 were positive and 1 were negative. Negative 2 is less than 5, but negative 1/2 is still less than positive a fifth. In order to progress with the algebra here, we are going to have to restrict our cases to epsilon less than 1, because that would prevent us from having a positive on one side and negative on the other. Looking back at the graph, if epsilon were more than 1, then this lower limit would actually be to the negative side. In a moment, I'll show what happens, both graphically and algebraically, if we allow epsilon to be greater than 1. We can work with that, but it's its own special case, and we have to think about that separately. But for now, as long as epsilon is less than 1, when you take the reciprocals, these are both positive, so we flip the direction of the inequalities, right? As I mentioned, 2 is less than 5, but 1/2 is more than a fifth. Subtraction just goes normally. So x minus 1, right, that's going to be our tolerance. X minus 1 has to be between 1 over 1 minus epsilon minus 1 and 1 over 1 plus epsilon minus 1. Realistically, this is going to be a positive number. This is going to be a negative number, right? This is more than 1, and we subtract 1, so it's positive. This is less than 1, so when we subtract 1, it's going to be negative. Realistically, this means that whatever our maximum tolerance in the x direction is, 1 over 1 minus epsilon minus 1 has to be more than that delta, or greater than or equal to that delta. 1 over 1 plus epsilon minus 1, that's going to be a negative number, and that has to be more negative than negative delta. Right? This sets a limit on our tolerance in the x direction. Okay. Before we get too far with this, what happens if epsilon is more than 1? If epsilon is greater than 1, you can see on the graph, both points where the curve intersects our boundaries, those are both to the left of our point. This one in quadrant 1, that's actually going to be more restrictive than the one out here in quadrant 3. Right? So realistically, we can just say this is going to be our cutoff. And since we know that epsilon is more than 1, this will be y at least 2, which means its corresponding x value will be less than a half. So what we can say is if 1 over x minus 1 is between negative epsilon, and we know that epsilon is at least 1, then we're saying 1 over x minus 1 is between negative 1 and 1. Add 1 to both sides. 1 over x is between 0 and 2. Notice everything's still positive here. I mean, as long as you're greater than 0, it's going to be positive. X just has to be some number bigger than a half. X minus 1, it's going to be some number bigger than negative half. So as long as delta is a half, right? If epsilon is greater than 1, then as long as we choose a delta that's at least a half, this will work. But of course, to show limits, right, we're usually worried about stuff happening nearby, right? Usually we want epsilon to be positive but smaller than some number, not too big. So getting back to the case where epsilon is less than 1, right? Still positive, but less than 1. We have these restrictions from 2 slides ago. And one thing that we can say, you're allowed to talk about this. Well, okay, we've got these 2 rules for delta. We can say this will work as long as delta is the minimum of these 2 numbers. Right? So either delta is just fine. If delta is less than or equal to 1 over 1 minus epsilon minus 1, okay. If negative delta is greater than this negative thing, that means that our original delta has to be less negative than that. So we can set delta equal to the minimum of these 2 numbers. And if we say x minus 1 is greater than the minimum of these 2, well, okay, that's going to be less than or equal to this one, right? I can pick either one. I'll pick the one that's going to make the algebra work out nicely. On the other hand, it's got to be less than the negative of this minimum. Okay, that's going to be less than or equal to this one. Or, sorry, I've got a sign error here. It's got to be greater than or equal to this. Subtract, add 1 to both sides. Add 1 to both sides. You get this? Remember, these are still always going to be positive. Take the reciprocal. And then when we subtract 1 to get our 1 over x minus 1, we get that that has to be between negative epsilon and epsilon. Now, if you don't want to factor in a minimum and deal with all this in your algebra, there's another trick you can use. Let's look again at this graph. Realistically, we know that the tighter restriction is going to be at the left end here, just because of the way that this graph curves. So can we just take this left end restriction, right? Can we just say our delta is going to be the left end restriction? And as a matter of fact, we can. Right? Suppose we set delta equals 1 minus 1 over 1 plus epsilon. So if we're saying x minus 1, on the one hand, it's 1 over 1 plus epsilon minus 1. On the other hand, as a matter of fact, we can. We can just say delta equals 1 minus 1 over 1 plus epsilon. So our x minus 1 has to be between delta and negative delta. So here's our delta, here's our negative delta. Remember, to take negative delta, you just switch the order of the subtraction. When we add 1 to both sides, this cancels out. This 1 becomes a 2. Take the reciprocal. 1 plus epsilon is, again, we flip the directions because everything here was positive. But 1 plus epsilon is greater than 1 over x, which is greater than 1 over 2. Again, we flip the directions. Everything's positive. So we have 1 plus epsilon is greater than 1 over x, which is greater than 1 over 2 minus 1 over 1 plus epsilon. Subtract 1 from both sides. We have our epsilon over here. We need to show that this gets bounded by negative epsilon. And to do that, we have to do some algebra to simplify this down. We start with a repeat of the line we had before. If we look at this compound fraction, we multiply numerator and denominator by 1 plus epsilon to get rid of this secondary denominator. It becomes 1 plus epsilon over 2 plus 2 epsilon minus 1, right? We multiply this 2 by 1 plus epsilon, we get 2 plus 2 epsilon. That simplifies to just a 1 plus 2 epsilon in the denominator. This 2 minus this 1 just gets us this 1. Then, to subtract 1 from this fraction, we want to get a common denominator. Then, to subtract 1 from this fraction, we want to get a common denominator. So we turn this into 1 plus 2 epsilon over 1 plus 2 epsilon. Recombine in the numerators, and when this simplifies down, we get 1 minus 1 and epsilon minus 2 epsilon. This becomes a negative epsilon over 1 plus 2 epsilon. Finally, this denominator of 1 plus 2 epsilon, that's got to be greater than 1, because epsilon is positive. Which means this is less negative than just negative epsilon by itself. And so we have our 1 over x minus 1 is going to be less than epsilon, but greater than negative epsilon, which is what we were trying to show. Yeah. So overall, this